Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at the University of California at Berkeley with Dr. Edward Lee, who's going to talk to you today about the Internet of Things and what they're seeing as both the vision and also the problems of getting to where we want to go.
One of the things that we're working on here at Berkeley is addressing a problem that we see with the way that Internet of Things technology is currently getting deployed, which has a very heavy reliance on cloud-based services. And we believe that it's a little bit too difficult to control the data that flows over the open internet. It's a little harder to preserve privacy. It's a little harder to control the latency. It's a little harder to ensure security. So we believe that actually the cloud infrastructure needs to have capabilities that are much closer to the end physical devices. So we kind of envision a family of new devices that we've been calling the immobiles, because they're comparable to the mobiles in kind of compute capability and networking capability. They have a bunch of wireless networking, perhaps wired networking, but they don't walk out of the room. They become instead part of the local infrastructure, and they can keep data local in order to ensure privacy, to improve security. And they can be used for applications that we like to call the Internet of Important Things, where you might care quite a bit, for example, about the amount of time that it takes between sensing something in the physical world and then taking some action in reaction to that sensing. So we've been working on devices that are, prototypes, I would call them, very early and crude prototypes of these immobiles, and we call them swarm boxes.
So let's take a look at one of these. So what are we looking at here?
Well, this is serial number 0001 of the swarm boxes, and we think of this as a very early prototype of what we believe will be something that will be a build-out of infrastructure, and that these sorts of the capabilities that go onto a device like this will become simply part of our local environment in much the way that Wi-Fi routers have become part of our local environment in the last 5 to 10 years. And our prototype here is designed for experimentation, so it's over-provisioned. It's physically much bigger than we expect these things to be eventually, but it has a number of radios on it. It's got two 802.15.4 radios on it. It's got a Bluetooth radio. It's got a Wi-Fi radio. It's got an extensive network of wired Ethernet capability, including some relatively new developments in Ethernet, which allows for tighter control of quality of service and more reliable routing. And we're using this box to figure out how a Internet of Things service can actually exploit the ability to do local computation instead of having to ship everything to remote services in the cloud.
What exactly are we talking about with a swarm box? What does that mean?
My vision is that the swarm box is it's our prototype of what we think will eventually go into the networking gear that you buy for your house, so or for a factory floor. So instead of buying a Wi-Fi router that just does routing of packets, we think that what is going to happen is that the network will actually gain compute capability that is much closer to the physical devices that it's interacting with. In fact, we believe that this is really essential for at least for the Internet of Important Things, because we need a level of reliability and we need a control over the quality of service in the networking that really isn't possible if you're routing all of your data to servers in some remote location. So one of the big challenges there, of course, is how do you develop services that have this kind of distributed computation. They're able to, we need to be able to deploy computations, to put computations close to the physical devices that they're interacting with.
So you're envisioning not just a single server or group of servers, but servers that are sort of evolving out of the device to the edge of the network, to the beyond the edge of the network, all the way into the cloud.
That's right. So these, I see these as fingers that the cloud puts out into the physical world. So the cloud gets compute capability and sensing capability and actuation capability that is much closer to the physical devices that it's interacting with.
So why are we looking at so many different types of radios and this massive redundancy? What are you trying to build in here? Is it more of an experiment about what works best?
Right. So we've architected this device just to facilitate our experimentation. So one of the things we wanted to be able to do, for example, is to be fairly aggressive about the software architecture that we deploy on the devices. But we're building out a test bed of these devices that will have several hundred of them scattered across the country. And we want to be very aggressive about experimenting with the way that we distribute software and services using these devices. And yet we want to be able to still interact with devices even if our experiments fail. So for example, we've endowed this particular prototype with 2 full-fledged computers. This is an Intel NUC that is running a standard off-the-shelf Linux distribution. And then we have a TI BeagleBone Black over here that we can use to deploy much more experimental software on. And if our experiment fails and the BeagleBone Black becomes completely non-responsive, we don't necessarily need to have physical access to the device because we can use network access through the NUC in order to, bring us back to a known good state with the BeagleBone Black. The BeagleBone here is communicating using radios, using a board that was designed by our colleagues at Michigan, and it enables direct communication with a variety of existing off-the-shelf Internet of Things devices, but we also have several other radios and network interfaces on this device in order primarily to facilitate experimentation.
What are you trying to measure here? Is it things like latency and also response time of how fast a sensor, for example, on a sensor subsystem can communicate with something else?
Yeah, that's a good that's a good description. I envision when I think of the Internet of Important Things, I'm thinking of things like a factory floor, where you've got networked sensors and actuators, but you're leveraging Internet technology to use your sensor data to control what's going on in the factory. So factory floors are safety critical environments. You can't tolerate the kinds of unpredictability that you get in purely information technology, where latencies are annoying but not dangerous. So we have to be able to exploit locality in order to be able to gain control over the network that is sufficient in order to be able to ensure safety of an internet technology deployed in that context. But there's other advantages also to exploiting locality. So if you keep your data local by default, for example, then you don't suffer from the potential privacy violations that can occur by just shipping your data over the open internet. You can reduce your security vulnerabilities also by keeping data local and keeping your control signals local on a local area network. So physical locality is something that we can really exploit in these kinds of systems.
What does this do for overall energy utilization? Overall energy expended as well as potentially saved in other places?
That's a very good question, and honestly, from the perspective of the devices themselves, I'm not sure, and I do worry about deploying a whole new infrastructure of energy-consuming devices. But my instinct tells me that the services that these devices provide give us enormous potential opportunities for making much more efficient use of the resources that are available to us. So I envision a world where every watt expended is expended for a human purpose. And right now we're really pretty far from that. We have buildings that leave lights on at all hours of the night even though they're unoccupied. I think broadly, Internet of Things technology gives us a way to correct for that, because it gives the information technology world eyes and ears into what's actually happening in the physical world, and then we can leverage information technology in order to just make better use of our resources, for example.
And what you're looking at here is not so much the what this grand vision will be, but how do we get there, right?
Absolutely. The focus of our research at Berkeley is not actually on the end applications. Our goal in these projects is actually to build the infrastructure that will enable then millions of creative people to come up with the applications. So by analogy, I think, when smartphones first appeared, none of us envisioned the kinds of applications that we now routinely carry around in our pockets all the time. We just couldn't have imagined that as technologists. So I think that the same thing is going to happen with Internet of Things technology, that there's going to be millions of creative people who are going to come up with ways of using this technology that we cannot imagine today. And our goal is to give them the toolkit that enables them to do that, make that creative use of the technology.
Dr. Edward Lee, thank you for some great insights into what's going on at Berkeley.
It's absolutely my pleasure.